Welcome to the lesson 1 of my Introduction to Quantum Computing course. In this video, we're going to cover bits, qubits, quantum computing, and all the fundamental concepts to get you started. So let's dive straight into the course. Okay, so we'll be going right into it. Today, we're going to be discussing bits, qubits, and quantum computing. To give you an overview of this course, there are going to be lectures every week. Homework is also going to be provided every week. The slides that I'm using in this video and the following videos will also be shared in the description box below. Along with that, there will be Jupyter notebooks that will be shared once we start getting into the programming aspect with Python and Qiskit. And at the end, we're going to be having a project as well. And for more details, you can check out this video. I've put the thumbnail over here of the video. You can check that out. It's on my channel for more details on the course. And this is just an overview of the content. There's going to be more content as well. Different algorithms, like Shor's algorithm, much more algorithms, definitely. More the math behind quantum computing, a lot of quantum mechanics phenomena, everything. And this is just a rough subject breakdown of what this course is going to cover. So there's going to be maybe 20% of this course is going to be the math portion, 20% is going to be physics, 20% is going to be Python and Qiskit programming, and then 30% is going to be coding algorithms, and then the last 10% is going to be a mini project at the end. Yeah, so now let's get into the first topic of this first lesson. We're going to be covering bits. So as you all know, classical computers, the term classical is being given to computers that are like our laptops and our mobile phones and supercomputers, just to differentiate them from quantum computers. So regular computers are called classical computers and quantum computers are quantum computers. So these classical computers run on bits, and bits are the smallest unit of data that a computer can understand. They are represented by 0 and 1, and they are actually the signal that a small amount of current is passed in the chip or not. So 0 signifies that either it is off, false, or this current is not passed. 1 represents that it is on, true, or this current is passing. Okay? And then these bits are what then make up bytes, and then megabytes, kilobytes, megabytes, gigabytes, all of that. Every text, image, video, whatever you see, websites are all basically bits. And even languages like Python, C, C++, Java, they all get converted finally into bits for the computer to understand and perform its work. Now let's get into qubits. So just like classical computers had bits as the fundamental unit of data, quantum computers have qubits, which are essentially quantum bits. So they exist in the state of 0, 1, and can exist in a superposition state of both 0 and 1. And I know that this definition of existing in both 0 and 1 is very common, but what does that actually mean? It means that after you measure this qubit state, when it's in this probability cloud of being a 0 and 1 at the same time, the chances of it being a 0 or a 1 may differ depending on the probability of each state. Okay, that is known as a superposition state. So you can have a qubit in a superposition state of a 50% chance of being a 0 state after measurement and a 50% chance of being a 1 state after measurement. You can have a superposition state where the chances of getting a 0 is only 10% and chances of getting a 1 is 90%. These are still superposition states. So when they say that a quantum bit can be a superposition of both 0 and 1, this is essentially what they mean. And now to represent the differences between a classical bit and a qubit, I have put this image over here. I'll take out my pencil now to make things more clear. It's like I said, a classical bit can be either 0 or 1. state, right? Only two states it can be in. But a qubit can be these classical states 0 and 1. So this point on the top is the 0th state of a qubit, and this point at the bottom is the 1 state of a qubit. But you can see that I've represented a qubit with this entire sphere. So this remaining part, apart from these two points, are the different superposition states that a qubit can take. And we use this sphere, which is known as the Bloch sphere, to represent the different states that a qubit can take. And you can see this axis over here is the 1 and 0th axis, which is easy to identify. We'll go into the details of the different axes. There are the x-axis, there's a y-axis, and there's a z-axis as well. So we can go into the details of that in the next lecture when I'm talking about Bloch sphere in greater detail. But for now, you can just understand that these different, any point on the sphere, if you can imagine a 3D sphere, any point on the surface is a different superposition state, where the chances of getting a 0 and 1 differ in each superposition state. Now, if you see over here, there's a third red arrow, which I just covered right now, which points to this. This is a state. This is another superposition state. And this is a state where the probability of getting a 0 and a 1 is equal, which is 50%. All right. So this comes when you use a Hadamard gate, which is, let me write that better. When you use a Hadamard gate, which is represented by this H symbol. We'll be getting into gates in the next video. X gate, Y gate, Z gate, Hadamard gate. There are different gates. Multiple qubit gates, single qubit gates, different things. Okay, we'll be covering that in the next video. But now for you to understand, this is more than enough. And now these superposition states and these qubits, when you measure them, they eventually come down to their classical states. Okay. Once you measure any qubit, they either turn out to be 0 or 1. But the chances of getting a 0 and the chances of getting a 1 may be different depending on its superposition state. All right. Now, another thing to keep in mind is that, just like I've mentioned in this second last point over here, that if you square the magnitudes of these amplitudes of the given probabilities of the qubits and you add them, that has to be equal to 1. And those squared magnitudes are the probabilities themselves. Okay. For example, if I take this is the most common state. Now over here, this coefficient and this coefficient is 1 by root 2, right? This indicates the probability of getting a 0 or getting a 1 after the measurement, right? So these states, you have to square them and take the magnitude of them and add them up, and that should equal to 1. So how would that come about? If you were to take 1 by root 2, and zoom in, yeah. If you take, oops, so if you take 1 by root 2, right? And then if you were to square this entire thing and make it positive magnitude, and do the same thing for this is just the state of here is just the probability of getting a 0. And now we move on to doing the same for the one state, right? And you square that as well. Okay, it's not clear. Right? If you now square, this is F squared, the probability of the one state as well. So if you square and add these, this should equal to 1. Okay, you can just add this and check it yourself. This will become 1 by 2 plus 1 by 2, which equals to 1, right? So this checks out. This is our condition. Alright, we'll be going into detail later, but for now, this is enough. Now moving on to what a Bloch sphere is. So a Bloch sphere is the 3D geometric representation of a state of a single qubit. Alright, this is just a representation. It's not a physical entity. It's not a physical entity or anything like that. This is just a mathematical 3D geometric representation of the different states that a qubit can be in. Alright, and these are the different accesses. Oh. Yeah. These are the different, oops. These are the different accesses. It's Y and Z accesses. Alright, that we'll be going into detail later. And your different your quantum gates can help change these and manipulate these qubit states and change it from one state to another. I'll give you an example of the X gate, which flips a state from 0 to 1 and 1 to 0. It is quite equivalent to the NOT gate, classical NOT gate. And suppose I were to have, right now I'm looking at a photo. Oops. Okay. Let me just take back. Anyway, suppose I started off with a zeroth state. I started off with a zeroth state, okay? Okay, yeah, suppose I started off with a zeroth state. This arrow just points to the state that the qubit is in right now. Okay, so in bracket notation, it would be I've started with a zeroth state. Okay, this is just the bracket notation, which we'll be covering later in the following slides. But for now, you can just see the zero in the middle, right? So just remember that this is the zeroth state. We're starting with it. And then I apply a X gate. Okay, this is what it looks like on Qiskit as well. And then the output for this gate is, it flips it to a 1. It flips a 0 to a 1 and a 1 to a 0. Just like a classical NOT gate. Okay. This is one of those examples where there's a commonality between a classical gate and a quantum gate, but most of the quantum gates are different from classical gates. Very different. So suppose I was going to start with this. With this zeroth state, okay, initially at this point, this is where the qubit is on the Bloch sphere, all right? And then I apply this X gate. And then what happens is, this does a 180-degree flip and then makes this arrow point here. So at the end of it, this is what your Bloch sphere will be showing. All right. This is pointing now to the one state, right? So one state from 0 to 1. Okay. These kinds of, there are a lot of gates. This is a very simple gate. This is the first gate that everybody learns, the X gate. There are multiple gates, single qubit gates, multiple qubit gates, two qubit gates, which we'll be covering in the next 2-3 lectures. But for now, just understanding this is more than enough. So we use this Bloch sphere just to be familiar with the different states and how gates affect these states. It's just a visual representation and to understand things better. All right, that is what we use a Bloch sphere for. Now let's go into what superposition is. Like I mentioned while explaining the Bloch sphere and what qubits can do, we were covering superposition over there as well. All right. Now to give you another example of what superposition is, I'd like to take you back to your chemistry chapters in high school, where we learned different electron orbitals, what shape they are, and which shell is what shape, is the s orbital, d orbital, p, f, all of that, right? So I'd like to take you back to that, picture yourself in that position. And now to understand this superposition better, that example will really help you, because I don't think I've seen this really covered anywhere else, but this is a good example. So these examples, I've put the different examples of the different shapes, the s orbital, different orbital shapes over here, right? So they were actually a probability sphere of where the electron can be found. Okay, so the s orbital, everybody knows, was this sphere. So that is the same thing that's happening when we're using the, let me go back. When we're using the Bloch sphere, that's the same concept that we're using. All right. These are the different states. Any point on the sphere points to a different superposition state of a qubit. And there are infinite states that a qubit can take, right? So now going back to chemistry class, when we were studying these different electron orbitals, they were a representation of where you could find your electrons in that certain orbital. So an s orbital, in an s orbital, which is this first example over here, let me zoom in, the electron could be in any point on this sphere, okay? But nowhere else. Electron can't be here or here or here, okay? Just within the sphere, right? But in this different orbital over here, the electron, there's a difference, right, between the s orbital and this orbital. The electrons are only, you can find them over here in this. This is again just a sphere. You can find the electron anywhere. That doesn't mean that the electron is everywhere over here, right? It's just a probability cloud or a probability shape, whatever you want to call it. You can find it in this part, but it is not in all these places at once. Okay. So that is a good example if you want to remember what superposition is, what a probability cloud is, all of that. This was just the example of the different operators, the order in which you have to fill them, right? Yes. Okay. So we use the Hadamard gate. That's a good example for beginners to understand, that which I had given you in the beginning. Now I'll give you, that was the X gate, where I was drawing over here. Is it here? Not here. Okay, see. Anyway, so the example that I was giving over here with the X gate, now I'll give you that example with the Hadamard gate to put an electron into, to put a qubit into the superposition state. Okay, so now you have, again, we start with the zeroth qubit, the zeroth state of the qubit, right? We're starting off, and then we apply a Hadamard gate, which is represented by this H, and then that transforms it into being, okay, this is too big to see right now. Let's zoom in. Okay. Yeah, so we're starting over. I'm still trying to get used to writing my fingers on my screen. Anyway, so we're starting off with a zero state and then applying a Hadamard gate, and then we get a superposition state, which can be represented like this. All right. So this you can see here, this is a zero state and this is also the zero state. And then since it's a superposition state, there has to be probability of getting one as well. So we've also put the one state here. And this number in the denominator, root 2, denotes that they are in a 50% chance of getting 0 and 50% chance of getting 1. Okay, this is an equal superposition state example, right? Now this might look a little complicated, but a simpler way of writing this is 1 by root 2 of 0 and 1 by root 2 of 1, right? This is that superposition state, okay? The main thing is that these coefficients, when squared and added, have to add up to 1, okay? So you can see over here, this is how a qubit state is represented, all right? Where this alpha is the probability of getting the 0 state after measurement, and beta is of getting 1 after measurement, all right? So when these alpha square plus beta square is added, you should get 1. You will get 1. Okay. Now going to this maze example, which is a very famous example to show how quantum can have an advantage over classical computing. So a regular computer, while finding the path through a maze, might choose every single possibility one after the other, right? In a list format. It'll choose one path first, then another, and go down all the possibilities, right? But a quantum computer can check all these possibilities at the same time. So that is done by the superposition property, okay? Where every path is checked at the same time, and once finally gives you, and that finally gives you the answer to the exit of the maze faster than a classical computer. Okay, that's a very famous example. Another very famous thought experiment is the Schrodinger's cat experiment, right? Where there is a cat in a box and there's a radioactive element, and then there's this acid, and then there's this counter that once the radioactive element decays, then this counter will measure it, and then there's a hammer to hit the acid, and then that will kill the cat. Now, this highlights how a quantum system can exist in multiple states simultaneously, but measurement forces it to define its outcome. Okay, and here the measurement being you opening the box and observing the cat state itself. So the act of measuring itself changes and alters the state of the cat in the box. It's quite counterintuitive, right? And that's why it's a famous thought experiment. Entanglement states that if two or more qubits are entangled, then doing any sort of change or observing or measuring any of these, one of these qubits immediately, instantaneously changes and alters the state of the other qubit. So if I were to entangle two qubits, okay, like in this image over here, there are two qubits over here. If I were to entangle these two in some way, and even if they were at the two opposite ends of the universe, and if I were to measure this qubit, and if the measurement would lead to maybe a zero state, okay, instantaneously the other qubit gets measured and shows the one state, the opposite of what you measured, okay. So if you got a zero state, it will show you one, and if you got a one state, it will show you a zero. Okay, so this is the unique entanglement property, and this is used in quantum teleportation, superencoding, encryption, cryptography, all of that. So why quantum computing? And this is, I'm not asking for what advantages quantum computers have and all that. Why did we need to come to quantum computers now? Because there was a physical limitation that had risen. Transistors, which are there in your classical computers, are these fundamental building blocks on your computer chip that passes this electricity and does this bit communication for your qubit to understand and perform complex calculations, right? So every year, the size of the transistors were getting smaller, and then the power of the chip was getting bigger. But then we reached one physical limit one fine day where making the transistors any smaller was making them function in a quantum way. Okay, now let's go into classical gates. So classical gates are logic gates that are used to do these Boolean and binary algebra on bits for classical computers. So we do these different manipulations with the bits to give the different electrical signals to do different tasks. Okay, so there's this AND gate, NOT gate, NAND gate, OR gate, NOR gate, XOR gate. There are more gates as well. So these gates are essential for binary manipulation for regular classical computers. And um, one other property of these classical gates are that they are irreversible. That means once you have an output from a gate, you can't trace it back to what the original input was. Okay, so if you've ended up with a 1, you can't really tell what state you started off with, which is not the case with quantum gates. So now let's go into quantum gates. So quantum gates are reversible. They're also known as unitary, which means reversible. And that is one key difference between a classical gate and a quantum gate. And here I've listed the different quantum gates, and you can find this image on Wikipedia if you just search for quantum gates. And this is the the X gate, the Y gate, Z gate. These are all single qubit gates. And so, yeah. So these are all single qubit gates, all right? Okay. These are single qubit gates. These are the names of the gates. These are the symbols of the gates. This is the name. Okay. These are the names of the gates, and these are the symbols. Okay. Now these are the matrix representation, which is the actual gate itself. They are made of matrices. So that's why you need to know linear algebra, matrices, determinants, probability, statistics, all of this to really do quantum computing well and really understand what is going on in these circuits, what these gates are actually forming. Okay, even the qubits are going to be in matrix form, and those matrix form qubits are then going to have matrix form gates applied on them, and they convert and form another output, which is going to be another matrix. Okay. So in the next classes, we'll be exploring what a matrix is, how to change one state to another, what the different gates are, what the qubit matrix is, what is a zero, um, how is a zero qubit um, depicted, how is a one qubit depicted, all of that, all right? So these are the ones that I've highlighted on top, are the single qubit gates. After that, we have the multiple qubit gates, which are two or more gates, all right? They are also in the same fashion, these are the names, and the symbols, and then the matrices. Great. Now this is a quantum circuit. So when we go into coding with Qiskit, that is when we will be seeing an image like this one. Okay, this is the qubit Q0, Q1, Q2. Let me get my pencil. Yeah, this is the first qubit. We always start with Q0. This is the second qubit, this is the third qubit. Okay, and these are the gates: the Hadamard gate, the X gate, and this is a symbol for measurement. Okay, this is the symbol of measuring. Okay, you get the point. My handwriting was not good, right? And this is a C naught gate. We'll be going into this in the third lecture. All right. So these are the different components of a circuit. You have the qubits, right? Over here, I mentioned over here, you have the qubits. Of course, you need qubits for your circuit. Then there are the quantum gates. So the next most important thing. Then there's quantum gates, and then your measurement. There are some more components to a circuit. You can have a barrier, okay, which I can put picture something like this. The components which will be also diving in when we get to the Qiskit coding part. For now, just understanding the different components of a circuit is good enough. Okay, so now we come to the bracket notation. So this is one of the most famous and widely used notations for denoting quantum state. All right. This is a representation of the bra state, and this is a representation of the ket state, and this is a bracket. Okay. This is a standard notation that we use for quantum states, and when you do an inner product, this is the representation of the inner product, bracket. And then the outer product is represented this way, which is a ket and a bra over here. Okay? Great. Now, how do you program a quantum computer? Okay. First, you start off by learning Python, learning matrix algebra, how the matrices work, all of that. And then you get into Qiskit or Circ or Penguin. These are quantum SDK software development kits made by IBM, Google, and Zonato. All right. So the the one that we are going to be using in this course is Qiskit. It's the most beginner friendly. So we're going to be starting with Qiskit, and we're going to be we'll start by defining our qubits, our circuits, then applying gates to our circuits, measuring it, running it, simulating it on the simulator, or running it on a real quantum computer as well. Okay, so this is how you run your program on a quantum computer. Now, quantum computers, if you haven't seen, I'm sure all of you would have seen an image of a quantum computer. This is like a standard image of a quantum computer. But the entire thing is not the quantum computer. These are just the different wires that are going to, over here there's the chip, which is the actual. Over here you can find the actual chip in the bottom. Okay, that is going to be here. Okay, and all the different wires are connected to it, to all the different functions. Okay, all these wires. But the chip is just like a regular classical chip, really small inside. And this entire body, this golden part, is known as the chandelier. Okay, and these are put inside a dilution refrigerator, which freezes these qubits because they have to work at the qubits. For them to work, there has to be a very, very, very cold temperature for it to function. So they operate at ultra cold temperatures, okay, and use dilution refrigerators to preserve the quantum state. And they are highly, highly, highly um, capable of getting destroyed by noise. Noise can be changing temperature. Anything can change and alter these quantum states. So they are very fragile. Hence the low temperatures and the dilution refrigerators. Quantum computer looks big just because of the chandelier, but the actual quantum processor is right over here at the bottom and it's really small. Okay. And yeah, speaking of which, these are the chips that have come out recently by Google, by Microsoft, by Amazon, right? These are what chips actually look like. And then on top of that, you have the chandelier. Okay, and all of these chips work on different technologies. Some are superconducting qubits, some are topological, others can be neutral atoms. Okay, in the next slide, we'll be covering the different types. I've just covered 4 types. I think there are more types as well. There's topological, with spin-based quantum computers. Okay, here we're just covering superconducting qubits, neutral atom, photonics, and trapped ion. Different types of quantum computers. Here we have the superconducting qubit type of quantum computer, which IBM and Google have. The neutral atom technology that QEra and Pascal are working on. The photonic quantum computers, which I think Xanadu and Psi Quantum are working on. The trapped ion technology quantum computers, which IonQ and Quantinuum are working on. Then topological quantum computers, which Microsoft are working on, and then there are spin-based quantum computers as well. I've not mentioned these two over here. Okay, so we'll be ending this lesson over here, and in the next lecture, we'll be covering qubits in more detail, what are blocks we can do, different quantum gates in more detail, what matrices are, how to represent a qubit in matrix form, how to transform them from one qubit state to another using different quantum gates, and just gates itself will take quite a lot of time. Single qubit gates, multiple qubit gates. Then we'll go into quantum algorithms, and finally we'll be making a mini project at the end. So this is going to take a couple of weeks, maybe 10 weeks or more to complete this. So stay tuned. And if you want to follow me, I do post on LinkedIn, Instagram, Twitter, and Medium as well, apart from YouTube. And I am more regular on LinkedIn. I usually post about 3 to 4 posts per week on LinkedIn, and Instagram and Twitter as well, and Medium as well. YouTube requires more commitment, so I tend to post one video rarely. But you can follow me on LinkedIn. That's where I'm most active, and I will see you in the next lesson.
Thank you for watching, and I'll see you in my next video.